Okay, so today the topic is relational databases. Have you guys ever heard of, you guys have heard of databases before, right? Yep. I mean, you know, like when it's really an important topic. I mean, anytime you use the internet to, you know, for example, like buy a product. I mean, you guys buy stuff on the internet, right? No. And the store, you never do. I always do. And you know, because the store has to keep a database of all their products with their prices, and you know, so. And anytime you do Google, you know, they've got a search. You know, you're searching database. So it's really an extremely important topic. And historically, different kinds of databases have been invented, but pretty soon they all kind of like converge to one particular kind called a relational database. Well, by history, I'm talking like decades, not centuries. But I mean, there is a history to computer science, and it does evolve, and we're still, the nice thing about it, the neat thing about computing is that it's such a young discipline compared to like physics and mathematics and chemistry. It's because the first electronic computers were invented in the late 40s, so it hasn't even been 100 years yet. And a lot of the stuff that is, I've been privileged to witness a lot of these big things that will be that people will be talking about for decades, you know, for another 100 years from now. Okay, so anyway, now what's interesting about relational databases is that we just learned about relations, right? And what is a relation? Row.
Set of ordered pairs?
Yeah, right. It's a set of ordered pairs. So that's a binary. So we've been talking about binary relations. Okay, so a binary relation, it's a subset of ordered pairs from, let's call it this time, let's call it B1 cross B2. Okay, so you know, B is one set and B1 is one set and B2 is another set, and the cross product is the set of all the possible ordered pairs, and then a relation is a subset of those. Are you with me? But look, you guys, now here's what's neat about relational databases. Instead of just having ordered pairs, you could have ordered triples, yeah. So that would be a trinary relation, okay? And this time, instead of being a subset of ordered pairs, it would be a subset of ordered triples, yeah. Be a subset of ordered triples. I would say trinary, but I'm not really sure. And so that would be the subset from what?
B1 cross B2 cross B3.
Yeah, B1 cross B2 cross B3. But of course, you can generalize this an n-ary relation. So binary, trinary, and then n-ary relation. Oh, yeah, n-ary. Yeah, it's actually a legitimate mathematical term.
Subset of ordered n's.
Of n tuples.
Yeah,
it's a subset of ordered n tuples. I never know whether to call this tuples or tuples. I've heard it pronounced both ways.
What?
Tuples. But I think it's n tuples. Triples, tuples. You say tuples, I say tuples. Oh, quadruple, tuple. Yeah.
So it really just depends.
It does just depend. You say tuple, I say tuple. You say tomato, I say tomato. From what? B1 cross B2 cross ... cross Bn. Are you with me? Now, and so in all practical relational databases, we have many more than just two. The tuple for practical ones. Okay, so now here's what we're going to do. There's going to, our author has an example, and he happens to be, you can tell by this examples in this chapter, he happens to be a Broadway musical enthusiast. Okay? And so the example that he picks is from, is information about Broadway musicals. Now, and so let's take a look at table 14.2. Notice here we have And table 14.2, it's called PABM, which stands for Popular American Broadway Musicals. All right? And let's just take a look at the structure of this table. How many items are in each row of the table? 6. So each one of those is a sextuple. Are you with me? Okay, so that's an ordered, each one of those is a tuple. Yeah? And the first one is the title. The first item in each row is the title of the musical. The second one is the month of the opening date. The third one is the day of the opening date. And the fourth one is the year of the opening date. So My Fair Lady is the first one. It opened on 3/15/1956. And then the next one is the theater. So it opened at the Mark Hellinger Theater. And the total number of performances, so we can see how popular the musical was, the total number of performances of My Fair Lady was 2,717. I'm not sure until, I guess maybe that's when it ran. I mean, obviously there's been a bazillion more performances since then.
Performances. Maybe that was the
That, I think that was the straight, yeah, when it first played on Broadway, that's probably what it was. All right? And then we have Man of La Mancha, Oklahoma, Hair, The King and I, Guys and Dolls, Cabaret, etc., West Side Story. All right? And then, so each one of those gives information about that musical. But now look at table 14.3. Table 14.3 is a different table, and what it has is for each musical, it has the book that the musical was based on, and then the person who wrote the lyrics and the person who wrote the music. So My Fair Lady was a Lerner and Loewe musical. And the other big one that you probably, you guys have all seen Oklahoma, yeah? Okay, Rodgers and, I guess they do music first and later. You think of it as Rodgers, you always hear Rodgers and Hammerstein, right? You associate that. So I guess that's a Loewe and Lerner as My Fair Lady. Okay, so here we have information about each one of those. Now, one thing that you notice, and the book doesn't really emphasize this very much, but in relational databases, there is always one particular attribute or column that is called the key. And can you tell oh, by the way, and this musical creators, table 14.3 is called musical creators, so we abbreviate that MC. But yeah, key. It's this. Yeah. So the key in PABM and MC. In PABM and MC, title is the key. And typically, what happens is in relational databases, you have one unique key. Can you tell me in the Pepperdine Student Information System, where they keep track of all your grades and your DIR, blah, blah, it's the campus-wide, CWID, the campus-wide ID. So they give you, that's a unique number, and so that's the key. So that's how the data is all keyed to that. So anytime there's information stored about you on the Student Information System, it's by your key. And why can't they use name? Because there's probably more than one John Jones who's attended, Yeah, I mean, there's probably several people with the same name, it's that's a unique.
Names are useless.
Yeah, we should all just be numbers, huh? How's it going? 79, 432? Man, did you see 65, 781 the other day? Anyway, okay, now here's another concept is called database design. Okay. Now, whenever you set up a relational database, what you have to do is you have to when you have a bunch of information and you're going to store it, you want to retrieve it, you want to maybe use it to as the basis of a website or something. You have to decide how to organize the data. Now, each one of these tuples, each one of these tables is a table, is a relation, okay? So, I mean, here, if we were to do this mathematically, this PABM, what we would do is we would have the relation, all relations are sets of tuples. So the relation would start off like this. It would start off with a set,
Right.
and then the first tuple would be, and then it would be my fair lady, my fair lady, comma, and then 3, comma, 15, blah, 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 and then in that tuple, and then comma, and then the next tuple, blah, 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 until the last tuple, and then it would be this. Okay, but we write them as this can be represented as a table, but these are really tuples, right? Is everybody clear on that? Okay, now, but now see, this is not the only way you could store this information. And as a matter of fact, it's kind of hard to, it's not too clear, unfortunately, in the book. But there are 3 database examples. Yes, there are 3 examples of database designed for this same data. You see what I mean? And whenever you set up a database, you have to design how you want to have the tables laid out. By the way, one of the most popular relational databases is Microsoft Access. I don't know if you guys have ever used that before. But that's, so if you've done that in another class, then this is, you should be familiar. Okay, so, but anyway, and I'm going to label these, capital A with a circle is PABM and MC. So that's the one that we just saw up there. Okay, the next one, the name of this database is all. Okay, now, actually, a little more information about PABM and MC. But I think we've already talked about it. PABM is title, cross month, cross day, cross year, cross theater, cross performances. So you see that's this n-ary, right? Does everybody, you can relate to this? Relate to this? Yeah. Okay, so we're not going to cut that. That was a good one. Okay, so that's PABM, and then this describes title, blah blah blah. And now the way we notate this, this database is we say PABM, the name of the relation. So that's the name of the relation, and then we give a descriptor for each one of the attributes in the tuple. Okay, so this is PABM and MC. But now this is not the only way we could do it. Another way to do it is we could do what he calls all. Now, unfortunately, he doesn't have an example table in the book, but I think you can imagine what it would be. All is just one table. Are you with me? All would it would just look like one table. And it would have the title, the month, the day, the year, the theater, the number of performances, the book, the lyrics, and the music. All on one row. And then it would all be, so this would be a 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be a 9 tuple. Are you with me? Or tuple, whatever. And I'm not going to bother to write the table, but you could write the first few rows of the table, right? You had to. Okay? And now a third one that he has is called where a third example of designing the data is this where, when, author, run, lyricist, composer. So this is the where, when, author, run, lyricist, composer. Now, can you imagine so how many tables would we have here?
6.
Yes, we would actually have 6 separate tables. Now, can you imagine that? And the first table would be named where, and how many columns would be in the first table? 2. Okay, a column for title and a column for theater. And then the next table would be when, and there would be. Okay, so I'm not going to bother writing those out, but can you imagine what it would look like. Okay? And by the way, notice here, now let's go back to this concept of the key. Notice that every one of these has the first column being the title. So the title is the key to the database. Also in this design. So the thing that I want to emphasize here is that these are 3 different designs for the same kind of data. So in the homework assignment, what you'll have is I'm going to ask you to do certain database operations on on a couple of with different database designs. Are you with me?
Yeah.
We'll concentrate mostly on A and C. But it just illustrates that there's more than one way to set up the database. All right. So so this is what a database looks like. This is an example of what a database looks like.
iTunes.
And
Biology.
oh yeah,
That's a database.
you're right. iTunes is a database.
So whenever
You
you
should
run
use that as your example because everyone knows why.
iTunes is.
like an advanced search and it asks you to put in information in all these different categories, is that really what it's?
Yes, in fact, it's very mathematical. As a matter of fact, now that you brought that up, how do you put? The question was how, when you query, that's called a querying the database. And there is a very mathematical. The reason relational databases are so powerful and so pervasive is that they have a very elegant, mathematically based, formal methods based query system. Okay, and so there are 3 queries. I'm glad you asked me that because that's what's coming up next. There are
It's still fun database to have.
no. Now, okay, so we're done with database design. Now we're talking about how do you access a database, a relational database. And there are 3 queries that you can make to a relational database. Okay,
Is that why it's called Microsoft Access? Because you access the database?
you access the database, I'm sure it is.
I never got that.
So, the first one is called select, and it has the mathematical symbol. What is this symbol?
Sigma.
Lowercase sigma. Select sigma, right? The English transliteration of that is S, Okay, the second operation is called project.
Yeah.
It's not project, it's project. And P, project, the Greek letter is? No, rho is R.
Oh, yeah.
P, project, pi,
Pi. I don't know the Greek
I can say it again.
lowercase pi. Ben was saying it from the very beginning, he wants us to know. And the third one is not a Greek letter,
Good pledge.
Well,
it's called join. And it's this bow tie symbol. So did you notice the bow tie symbol on at the very first day when we, in that table, there's the bow tie is one of the binary operators. Yeah, it's called the natural join. Okay, now, and so what we're going to do is see how what each one of these does. Okay, now let's go over here to your equation sheet. So your equation sheet does have these 3 queries defined as 3 definitions. 14.56.1 is the definition of select, 14.56.2 is the definition of project, and 14.56.3 is the definition of natural join.
These are not in the book.
Well, I think they're in the book, but they're not numbered.
Oh,
They're,
so you know.
so I numbered them, and I put them in a nice little thing for your equation sheet. Okay, you're welcome. Now, here's the thing. So we're going to go over, let's take a look at each one of these definitions. What's interesting about this is that we can actually write, it's very Gesundheit. It's very easy to write a formal definition of select and project, but it's really hard to write a formal definition of join. So the definition of join is kind of a little bit informal. So anyway, before we see actually what each one of these does, let's take a look at the structure of it. Okay, so first we'll take a look at, and then we'll do some examples. All right. So first of all, select. Now, check out what select is. Sigma is, we have sigma parentheses R comma F. Now what the heck is
Where
this?
R is a relation and
R is a relation and F is a what?
Predicate.
Is a predicate. Okay, now, do we remember? Okay, so, oh, actually here we go. So sigma, so here we have sigma R F. And what we're saying here is that, okay, so this R is a relation, and this F is a predicate, okay? Now,
What's the predicate?
what, how did you know I was going to ask what's a predicate? Because I always ask what's a predicate, especially now when we know that F is, we're saying F is a predicate. So what's a predicate? Don't tell me you don't. Don't tell me, are you looking something up? Are you telling me you have to look this up?
Boolean expression.
it's a
No, no, no.
No.
It's a function that returns type Boolean.
It's a Boolean function.
I thought you said expression. Yeah, yeah, you can't, yeah. Yeah, proposition, yeah, okay. So a predicate is a function that returns type true, okay? Now, can you tell in here, can you tell by this definition what this is? It's the set over T such that what?
T is an element of-
T is an element of the relation. So now what is a relation? How can you think of a relation? As a table, right? So it's a set of all those, and remember oh shoot, I erased it. Remember it's the set of all those tuples, but such that T is in the relation, so it's a set of all of the ones, but such that not only T is in the relation, but also what?
The function returns.
Yeah, for which that is true. So is it going to be, generally, it's going to be what? It's going to be like, you're going to select certain rows based on this function. So the sigma of the relation is the same as the relation, but probably smaller with fewer rows. And so you select based on this criterion. Are you with me?
Oh, would that be like in iTunes when you like type in a search up the top and it gives
Yeah, and it only gives you the one that is a select. When you type in a search and you type that in, that's a select.
Yeah.
And it's, so if you type in the title,
predicate, right? That's-
well, what you're doing is it's equals whatever you put in. It's the title equals whatever you put in.
Okay.
Yeah.
Cool.
All right. So that's the idea
Yeah,
behind.
but that one, that kind of searches the title. It'll match up like
It not only the title, it might also well. So what it does internally is it takes
this, all this.
exactly. It does title equals this, or title or composer equals this, or whatever equals. So, but internally it does it.
That's kinda cool.
It goes it expands it out.
Yeah.
Yeah. Okay. So that's select. Now project. Let's do project. So so now what's the structure of project? It's pi. And now what do we have inside this pi? We have an R, okay, and then what do we have? A1, A2, dot, 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 A sub M. Right? Now, what the heck are these things? So now what we have is, this is kind of interesting, huh? So the first one, again, the first one is a what? The first thing is a what? Is a relation. Okay? But the second one is, now what are these things? These are, can you tell from that what they are?
Subset of the names of the.
Yeah, of the columns, yeah. Those, the A is attributes, those are called attributes. So this is a subset of the fields. Those are sometimes called fields. Subset of the fields. Okay, so basically what is the project doing? And whereas select was taking out what? What was select taking out? When you do a select, what do you take out? in the table, what do you select that?
Stuff that the predicate's false.
You select certain rows and you leave other ones out, right?
Yeah.
Are you with me? That's what select is. Now, what does this say project is? What is project doing? That is projecting out the columns. All right? So what you're doing here, what you're doing with the select is you're getting rid of some rows, but what you're doing with project is you're getting rid of some columns.
Oh, okay.
Are you with me? Is that clear? All right? So it's no longer a tuple. See, if the original one is an n tuple, this table won't be a table of n tuples, it will be a table of m tuples, where m is less than or equal to n.
Yeah.
Are you with me? Is that good?
Yeah.
So in both cases, we are actually, now think about this for a minute. Does everybody see that a sigma of a relation is another relation? Now this is a powerful idea. This is why relational databases are so powerful. It's because when you do a sigma of a relation, you get another relation. And furthermore, if you do a project of a relation, you get another what? You get another relation. So do you see then that you could sigma, and then inside here could be a what? A relation. It could be a project. Or a project, you could have a sigma in here.
Like with the iTunes, back to iTunes search, that's
You-
like type in one name and it gives you a chunk, and then you keep typing and it.
And it says all, yeah.
It's like, kinda cool.
Okay, and does everybody see how this works? What we're doing? Okay, now both of these, and one of these are taking out rows, and another one you're taking out columns. So in both of them you're taking it out, and there's no other way to take out. There's only rows and columns, right? But in order to make a database be powerful, one of the things that gives relational databases their great power is that we have this third operation, which is called natural join. So with natural join, what do you assume? Now join means somehow doing what? Taking two separate relations and somehow putting them together. See, because if you can winnow out by row and by column, then to be once you can winnow out, and then once you can put them together, then any query can be,
And that's how you get really like specific responses, like using the natural join on different selects and projects.
Yeah, and we'll do some. Yeah. Okay. So the third one is called natural join, and we don't have a way to do it we don't have a clean way to describe it, to describe the structure of it like this, but the natural join. So the natural join, and furthermore, with the natural join, check this out. What kind of an operator is this?
Binary.
Yes, binary infix is an infix, is a binary infix operator. So what do you think? And furthermore, what does it operate on? What is the relations? Yeah, relations.
Just that.
So what did we have? R. We could say like you could say like R join Q, right? And the way this works now is that both of these are relations. Now, I've written it out here in English, so let's take a look at our slide again. 14.56.3, definition of natural joins. Oh, I guess I should have done R1, R2. Well, RQ, whatever. Okay. So for relations R1 and R2, R1 join R2 has all the attributes that R1 and R2 have. Now, what is an attribute? All the R2D2. All the columns. So the join has all the columns of both of them, all right? But if an attribute appears in both, like if it appears, then it only appears once in the join. Okay, so you don't want to repeat an identical an identical attribute. That would be redundant, right? Are you with me? So there's that. Further, now that one's not too bad. Further, only those tuples that agree on this common attribute are included.
What? That agree.
So that one thing.
So that one thing that's in common, that only appears once.
I know, that's the only thing that appears.
No, no, hold on. That column only appears once, but the rows that appear only are only the ones that agree on that column. So typically there's one column that appears, there's never more than one. In practice, there's always one column that appears in both. So it joins on that column, and all the other columns are included, but that column is included only once. But it's not. But the only tuples that are included are the ones that have that one in common.
So if you,
Which is what you would. I mean, when you think about it, it's what you would expect. Yeah. Now, right. So now what we have to do is we should do a bunch of examples to see how this works. Okay. So now, so let's do a bunch of examples. Okay. So here we go. Let's use A. So let's go. Okay. So now we're going to use these databases that we defined before. Okay. So let's use A to list the 6 tuples that opened on 46th Street. Use A to list the 6 tuples that opened on 46th Street. That opened on 46th Street. So let's go back to A and see what we have here. So if I just asked you, if you just looked at this and I just said, which musicals opened on 46th Street, what would you say? Yeah, Guys and Dolls and Damn Yankees, right? I mean, you just sort of, but the question is, how do we get a table? How do we get the table that just has that just has the ones that open on select? Okay, so it would be, so here's the solution. All right. So if I ask you to do this on the homework, here's what the solution would look like. So select. So sigma. Now what's the relation that we're going to use? No, that's not the relation. PABM is the relation. Is everybody clear on this? The first thing has to be the relation. Are you with me over here? Okay, so it's PABM. So that's the name of the relation. That's the table. And now what is our predicate?
46
What about 46?
equals theater?
Yes, exactly. It's theater equals 46th Street. That's it. That's the query. Are you with me?
Yes.
Okay. Now, how about this? Now, what would this table look like? This table would have 2 entries in it. The first entry would be Guys and Dolls, 1124, 1950, 46th Street, 1200, and the next row would be Damn Yankees, 55, 1955, 46th Street, 1019. Right? Now, how about this though? So our second problem is this. 2. Use A to list only the titles of those that opened on 46th Street. To list only the titles of those that opened on 46th Street. Now, how are you going to do that?
Well, you need to project something.
Yeah, you're going to have to project out the stuff. So how do you? Well, what did we do? Well, what do you want to project? I gave you
I
a.
want to project the titles using that.
That relation.
Yeah, this.
That expression will be the for the project.
Okay, exactly. Okay, so we'll project. So we'll project. But see, now this is the beauty of, this is the power of relational databases. This query is a relation.
Yeah.
Is that cool? So pi of what? Of sigma of, and look how formal methods this is. Pi of sigma of PABM.
Discrete structures.
Yeah, this is way total discrete structures. Theater equals 46th Street. Theater equals 46th street. Okay, street, parentheses, so that's the R of the pie, and now what's the structure of project? What do we put here?
Do we put what we want?
Well, we list, see, what we do is we list the attributes. Is everybody clear on this? Yeah, just the it said just the titles. So the name, so that attribute is called title. You see on the table, it's title. So it's just comma title. See, this is an interesting function notation because it takes an arbitrary number of arguments here. All right, you don't know ahead of time how many attributes you're going to have here. Is everybody clear? Okay.
As a relation, the rest are all.
Yes, that's a very good observation. The first one is the relation, and then the second one, and however many more after that, have to be attributes, not elements, attributes of this relation. So the computer can check to make sure that what you put here is an attribute of this relation.
Field, the attribute,
Yes, field and attributes are the same thing.
what's the,
Yes, and if you wanted the theater as well, it would be title, comma, theater. Uh-huh. All right? Now, the third one, let's go to a different database. Let's go to database C. All right? So let's use C to list where each book was performed. They always, everything is a relation.
That one returns a relation?
Absolutely. Absolutely. Everything returns a relation. Okay? So, check this out. Let's use C to list where each book was performed. Use C to list where each book was performed. Okay.
I'm guessing when you
Now, to list where each book was performed.
We need some join.
We're going to have some join, and you're right. We're going to have some join because here's our, let's take a look at
we have two different databases.
We need to
no, we have this, no, hold on, let's be clear about this terminology. This is a database. It consists of 1, 2, 3, 4, 5, 6 relations.
Okay.
So this is how our data is organized in this database.
Right.
All right? But it has these 6. Are you with me? Now, we're asking to list where each book was performed. So obviously we're going to have to join what?
Where and author.
We're going to have to join where, which is the theater where it's performed, and author. Okay? So let's just imagine. So can you tell me this? Author, can you tell me this? Author, join where? How many columns does it have? Has 3 columns. Are you with me? And just to make this very concrete, author has what? Title book. Where has what? Title theater. Now here's an example of the join. Okay, so check this out. So here's what our table is going to look like. We'll do the first row of it. So it will have title, okay, because that one's common, right? And then it will have book from one of them, and it will have theater from the other one. Are you with me? Okay? And now, the first row of this will be what? We have to go back in. Now, you see, it's not anybody's title with anybody's book with anybody's theater. You see, it's not a title with any book in any theater. The book in the theater has to match the tuple, the one that's common to this. Okay, so let's go back and see what that would be. So the title would be My Fair Lady. So here, the title would be My Fair Lady. Okay. So book would be Lerner. And theater would be what? Mark, what is it? Okay. And then ... Right? Now, to get just the book, okay, so that's what that is, all right? Now, to get just, I'm going to erase this now because we're scrolling. To get just the book and the theater, we project. To get to get just the book and theater project. All right, so so what is it? So therefore, what's the final solution?
Pi.
Pi, okay, so it's pi, and then what? Author join where? Yeah. Author join where? Comma,
Book, comma.
and then book, comma, theater. Now, how's that for some discrete structures? That's super practical. So don't ever say this is not practical. And you know, when you guys study relational databases, there is a huge, you know, this actually defines an algebra, pi and project, select, and join. It forms an algebra, and there are theorems and blah blah blah, and it has a big mathematical structure, and it's all based on relations, which you know now. You know what a relation is, a subset of. Yeah, and so you could pick up a relational database book now, and you'd be well introduced to the concepts. You could just go through that and learn all the ins and outs. There's a huge theory of relational databases, and not only that, it's interesting because I've given you three different. Here's another interesting thing. We've given you three different examples of how to design a database. There are database. I mean, if you study relational databases, one of the things that you learn how to do is there's a process called normalization, and there are techniques for how to design a relational database, how to set up the tables so that you don't have redundant information, and so that you know the most efficient way to do it, and you pick the right keys. I mean, you know, there's a whole discipline of how to design databases. But now you've got the basics. You know, you can understand. You know what some of those issues are. There's this thing called normalization that's very desirable characteristic to have, and one of the things you learn when you study database design is how to normalize a database. Okay, well, let's do one more example. We're back to A. Use A to list. Okay, last example. Use A to list who wrote the lyrics. Who wrote the lyrics? I know you won't use proofs, but on the other hand, you will. On the other hand, knowing how to prove is it's the thinking of how to, and it relates directly to programming. Okay, so it's not you might not ever prove it. You probably won't. You know, you might not ever prove that a program that you wrote is correct. But if you learn the concepts of an invariant and you know, and how to, anyway, off topic here. Sorry, lyrics. Okay, for the show that had 2717 performances. That had 2717 performances.
I can just tell you that.
I know you could just. Isn't that something you could just tell me that by looking? But now, how would you actually query the database to do that?
Query for the exact number of performance.
Well, okay. So first of all, the problem is
Where's the lyrics?
You have to join them,
you do have to join.
because the lyrics are in the other.
Yeah. So what do you have to join?
Join PABM.
PABM. Okay, so let's join. So let's do PABM, and let's join that with MC. Okay. Now, once we do now can you imagine PABM and MC? Can you imagine what that table looks like?
Yeah.
For the time.
Well, we
Oh,
wanna
we're doing a
select-
projection and
Okay, and now from that, and from that, what do we want to do?
you can do either
Select.
or, right?
Yeah, think about that.
Order-wise.
Okay, let's do it. Let's do select first.
Yeah, it says select.
Could you do?
Yeah, think about that. Seems like you could, huh? Okay, so now what should we select out?
So that performances equals whatever that number is, 27.
Perfs equals 2717, right? Okay, and so we want to select that.
I'm going to project lyrics.
And then we want to project lyrics. So we project this
That's cool.
with lyrics.
Or we could,
So,
no, I don't know.
put that in your pipe and smoke it.
Could we do it the other way around?
Yes.
Because if we project just lyrics,
Yeah.
You use the lyrics to project.
but then we don't know what the perfs is.
Ooh.
If we project lyrics and perfs,
Yeah, that's a good.
then we're selecting both of them, and we don't want both.
Well, you think about it. That's it.
I'm going to my.
Okay, good deal. We're actually going to go on to the next chapter next time. See you tomorrow.